It's good because what awaits us now are the RICAIP Demonstrators, from research to industrial reality. So forget PowerPoint presentations. There might be some, but there will also be physical things to show you, either in form of video, virtual reality, and then of course you can tour the test bed afterwards as well, and I really strongly encourage you to do that. The first person that I wanted to join me on stage, and I'm looking for him frantically, is Pavel Burget. Where are you? Ah, there you are, looking sharp as ever in your suit. I'm always used to a t-shirt only, but you look fantastic. It is great to see you, and we would love for you to be the first person to show us the RICAIP demonstrator with the video going first. Yes? Thank you.
Thank you, Sarah. So, as Sarah said, we are going to start with the video that we prepared to summarize the main idea of RICAIP, which is distributed, or we also often say flexible production. So, I hope the video starts soon.
Today's production must respond faster than ever to changing demands, shifting conditions, and unexpected disruptions. At RICAIP, we explore how manufacturing can truly adapt compared to traditional planning that still relies on a single, ideal scenario. In reality, however, capacities change and resources are not always available.
Manufacturing as a service offers a different approach for more flexible and resilient production. RICAIP provides a unique infrastructure connecting Czech industrial testbeds in Prague and Brno with facilities in Saarbrücken and Kaiserslautern in Germany for developing and testing these scenarios. Instead of fixed plans, production is organized automatically in real time based on what is available.
Let's demonstrate this through the production of a modular product manufactured using multiple technologies across connected sites. The core of the production takes place in Prague.
Advanced technologies such as 3D printing, machining, and automated assembly are used to manufacture and integrate key parts of the product. The execution of each operation is continuously coordinated by a central system.
At the center of this process, there is a manufacturing execution system, or MES. It defines the workflow, assigns operations to available resources, and synchronizes all steps in real time. By selecting a product variant, the entire production is configured and planned automatically using advanced methods such as graph neural networks.
The test bed in Saarbrücken demonstrates a multi-agent system for production execution, showing that not only individual machines, but also complex systems can be integrated using standardized interfaces with defined semantics. The test bed in Brno is one of the production sites. It manufactures specific components and enables remote process inspection using an autonomous mobile robot.
All components are brought together, showing how manufacturing as a service operates as a unified system. This is enabled by standardized interfaces based on OPC UA and MQTT, real-time data exchange, and the integration of existing machines into one coordinated environment.
Coordination is handled automatically using modern methods based on machine learning and AI.
What makes this system powerful is its flexibility. Operations are not fixed to specific machines or locations. They can be reassigned at any time based on capacity, availability, or changing requirements. If one resource becomes unavailable, the system can automatically find an alternative way to complete the task.
For companies, this means greater flexibility and faster response to changing conditions across the entire value chain. The manufacturing as a service concept has been demonstrated with T-Process platform and industrial MES deployed at many sites, making adoption in real environments straightforward.
From coordinated operations to a finished product, RICAIP transforms manufacturing from fixed planning to an integrated, flexible production, ready to adapt to current challenges.
So this was the introduction of the idea, and actually the idea that was at the beginning of RICAIP and that was, let's say, accompanying us for the whole duration of the project. Now I'm going to go a little bit more into the technical details that will show actually some pieces of equipment that are part of our testbeds, but also talk more about the concept how machines are interconnected into bigger systems and then to individual sites. So the state-of-the-art production is mainly controlled intuitively. So there is no flexibility. Typically, there is no flexibility in how the production is organized and how the production is controlled. So when there is a planning performed by a manufacturing execution system or an ERP system, it's often based on infinite capacity assumptions, so that we do not expect any disruptions, any failed buffers, and so on. So no alternative work processes are available very often. Moreover, the machines do not publish their capabilities. So it's very difficult to learn or to read what a machine is capable to produce. Which means that such a system is can react very hardly to disruptions, to changes such as machine failure, to changes in the supply chain, and so on. So, therefore, flexible manufacturing, which allows to combine the current status of the machines, which here we say that it's machine monitoring, and production planning. So by combining what we know about the current state of the process with what needs to be produced, we can adapt and generate production plans, production sequences that are adapted to the actual situation. So it combines the machines, then the capabilities, what can be produced by the machines. All this is put together in a planner and then executed in a manufacturing execution system. So as an output of such a workflow, there is a production plan with selected routes, but also with alternatives and scheduled envelope for the actual capacities. So this is the idea and how we implemented it. These are main blocks of the solution, which consists of the machine data and representation of the resources or assets by using asset administration shell, which actually is one of the key concepts of Industry 4.0 from its very beginning. And of course, we need to have standardized interface to the machines to provide commands to them, but also to read the status, to read the actual information, what is going on there. Then we want to match and explain how this can fit together also with the requirements of the products, what needs to be produced. So these are the capabilities, availabilities, and it's matched to what is needed. Then dispatched to the manufacturing execution system to execute the commands, provide some operator view over the dashboard, and have the possibility to replan the production when conditions change. I would like to emphasize a synergic project, RACEMAN, which focuses on manufacturing execution service, which focuses on manufacturing as a service, and our participation is based to a very big extent to what RICAIP created. This is an infrastructure of interconnected testbeds that are part of RICAIP. So you can see 2 testbeds here in Prague, upper and lower testbed in CEITEC, and testbed in DFKI. Each of the testbeds has its own system with standardized communication module, and there is a multi-agent system in DFKI, which in fact represents that it's not only about a single system, but it can be a set of systems that are interconnected, but to the outside world, to the world of interconnected testbeds, such a system is understood as a single component, even if it is complex. What you saw in the video was demonstration of how a simple product can be produced, but the demonstration is important because it relies on all those principles that have been mentioned. So simple maze, which consists of production operation as well as assembly operations, and these are the individual subparts with steps that needs to be executed, and in fact this is the route for the product to be produced from a single subparts to the final product. So these are described as bill of material, then bill of operations or bill of services, capabilities that the machines provide, commands and status for the individual machine. So now we are at the level of single operations, which can be executed by specific machines at specific sites. So just a short, let's say, view into what machines are available and what machines participate in this specific production of in this specific demonstration product. So you can see machining centers here in the lower testbed with some capabilities like milling, drilling, and so on, and status objects that represents the status of the machines, and the production capability that is important for the product is here, so manufacturing of the base. Production capabilities in CEITEC include 3D printers and machining center as well, so you can also see the capability objects, status objects, and for our specific case, these are the capabilities that are offered to the network of interconnected testbed. And the capabilities here in the upper testbed in Prague mainly consist of assembly, transport of the products, inspection, and final release of the part. So these are the individual sites, 3 sites interconnected through standard interfaces, asset administration shells, and advertisement of the capabilities. And in fact, a unified data model was created to standardize the communication. So I mentioned it several times that it's based on asset administration shell, which allows other sites to be included easily using the same standard interface. So it's about the assets, but also about the real-time communication by using real-time OPC UA, mainly OPC UA standard. Production planning is a crucial part of this. So we take the bill of service, we take the required operations, in fact the technological RICAIP, match it together to see which resources can be used to perform specific operations, create a plan based on the capacity and based on the capabilities that are available, and then dispatch the commands to the manufacturing execution system or through the manufacturing execution system to the machines. You can see just a short view on the sort of knowledge graph that represents the resources and which is used as the core of the planning algorithm in our case, which is an example how such an automatic planning can be done. But because all the system is open, we can also connect other algorithms, other tools that can contribute to the automatic planning capability. What is important is that we do not end up with the demonstration product that was shown here. So it's just a demonstration, but we of course have a plan how to scale up to real industrial deployment. So you can see an example that represents deployment at several factories or several sites, several production lines, no matter how we call it or to what extent we go. You can see the list of operations or list of steps that need to be taken at each site, and through this we can in fact build a network, manufacturing as a service network, where individual participants are present, and all the, let's say, order planning, capability brokerage, local execution is performed automatically. So this is the idea how to scale up. We have first a real example of industrial deployment in cooperation with T-Business, which is an industry division of T-Mobile. And after the pilot deployment, we expect commercial operation. So to summarize, we did not spend the years in RICAIP by buying machines and by, let's say, playing with demonstrations, but we realize very thoroughly that it's important to bring something to the industrial companies, to introduce innovations and to utilize the infrastructure, to utilize the effort to utilize the effort also for the good of the industry. So thank you for the attention.
Thank you very much. Yes, and within our maze, we do not have a minor tool, but we have beautiful product of interdisciplinary friendship and collaboration. So thank you very much, Pavel, for leading the charge on this. And again, I would like to invite you later to actually tour the test beds. We now have the next gentleman who I'd like to invite up here, and that's Professor Luděk Žalud from CEITEC, who will show us the RICAIP demonstrator from the other side of the Republic. Thank you very much. Oh, that was an Olympic leap. Thank you.
Hello, good morning. Thank you for invitation to this conference. So I'm going, can I switch it by myself? Okay, I will try it. Yeah, it works. So I'm going to speak about remote robotic inspection of industrial facilities, and I will demonstrate it by two independent machines, robotic machines. The first one is our Odin robot, which was built for RICAIP project, and it was built really for industrial facilities. So it's a machine that is only able to work inside buildings, in flat surfaces. It has so-called omnidirectional wheel, so it can move in any direction. And the payload capacity is like 300 kilograms. And the second one is completely different machine. It's a walking machine, quadruped from Boston Dynamics, which was only developed, which was not developed by our team, but we only added our equipment on board this robot. So what we are going to speak about is kind of strange combination of fully autonomous machines that have all the robotic stuff like trajectory planning, obstacle avoidance, 3D scanning, and so on, together with telepresence principle, where we've got a system that is able to help with remote inspection of inaccessible or dangerous places, or basically only some kind of features that we want to see inside the building. So this is just kind of, in principle, strange combination of fully autonomous machines with telepresence control. So firstly, just a few words about autonomous mode on board the Odin. So we've got all the stuff that robotists do like to use, like 6 Livox mid-70 3D lidars on board the robot that can sense fully 360 view around the robot. We've got our own onboard computing machine based on Intel NUC with Ubuntu system, and obviously we've got couple of algorithms based on local and global coast maps, A-star modification, and so on for local and global planning of trajectory. Everything is based on ROS2. What's also important, even if the calculations are done on board the robot, which is very important because of latency and so on, we are able to remotely make the path planning of the robot, which is very important. And what's also important, since we are moving in industrial spaces, we think about safety. So there is like kind of a remote control switch which fulfills SIL standards, so it's really quite safe. So what's the telepresence principle on board? Well, the principle itself is quite standard. What might be quite interesting, we've got something on board the robot, I will speak about it later, but what is interesting is the operator's part, where we've got two basic approaches that we can use. The first one is that the data that are transferred through half of the planet, if necessary, can go directly to the head-mounted display. The head-mounted display itself has its own like calculation capacity. It has Android processor on board, so it can do something, but it's not that powerful. So the other option is that we can go through PC and make everything more safe, faster, with lower latency, with higher resolution. So we've got both of these options available. Since we are really heading towards high resolution and high-end telepresence, we have decided to build our own electronics on board the robot to grab the data and get all the stuff to be really fast and with low latency. So we have built a combination of NVIDIA Jetson, with its really high computational capacity, with FPGA that is made to get the data as fast as possible from the cameras. We are able to get the data from up to 6 cameras. Each of them can be different, and yeah. We were also forced to build our own software stack, which is based mostly on C and C++, and some parts are also made in Python. Then we've got the real physical hardware. We've got two approaches that are interchangeable, which is very important. The first one is articulated camera head. With 2 degrees of freedom, so we have built our own manipulator together with a motor company, TG Drives in Brno, which is really ultra high speed, very precise with low latency, so it's basically able to copy the movements of human's head. And what's very important on this one is that it is possible to have stereo vision on this one. Yeah, so we've got 2 cameras, and you have really highly immersive stereo vision system. What's also important, it's completely independent, or it may be completely independent on the robotic platform, so it's really fully detachable. So it has its own battery power, but also its own communication, and that much doesn't matter whether we are using 5G, Wi-Fi, MANET, or whatever. So it may be really completely independent on the robot. The second one is what we call solid-state camera head. It's based on 6 cameras that are solid-state, they are not moving, and they've got like 360 view around the machine. Obviously, as everything, this has some advantages and disadvantages. The main advantage is that it has no moving parts, so it's really reliable. It can work in industrial spaces with high vibrations and such a stuff. Obviously, it also doesn't have this annoying problem that all the mechanical subsystems have, that you have to firstly move somewhere and then you can see it. So this one is instant, so this part of latency is not in here. But the biggest drawback or disadvantage of this approach is that there is it's not possible to have stereo vision with such a subsystem. Again, this one is also fully independent on the robotic system. We can put battery, we can either connect it wirelessly or through wire to the robot. So, and what's again very important, they are interchangeable. The dimensions are completely the same. Since telepresence is mostly about communication and about its parameters, so this communication scheme is really vital part of the system or its description. So we've got this part which is on the test bed with the robot, where we've got the robot itself, the detachable head. They communicate somehow through ROS. There is Jetson in here, which grabs the data basically and is able to compress them and send them somehow to the other testbed with the operator. What's very important is this IPsec tunnel. We are still heading towards something that needs to be really reliable and not easy to be hacked. So we can basically use whatever communication infrastructure since everything is highly encrypted. So we can use 5G, optical cable, whatever. And on the operator side, we've got this kind of complicated scheme of communication with some video streams, robot control streams. And what's very important is this last part, which was added just recently with OPC UA communication, which makes it possible to connect the robot to the testbed infrastructure and to be really part of the infrastructure. So this is how it is done. This is an example between Prague and Brno, where we've got like mesh system in Prague with OPC UA client, and again from some VPN, some secure way of communication, we send the data to testbed in Brno. Here we've got the server, but because we've got two kinds of machines in here, the first ones are what I would say natively speaking OPC UA language, are just connected through OPC UA bridge towards the rest of the world. And then we've got machines that are basically our robots or simulators that are not speaking this language. And for this, we've got this web server that is able to make translation, easily saying, between these languages. So this is the complete description of the mission. So we've got an operator who might be in Prague, for example. This is OPC UA screen or interface screen. He or she, in this case, just switches a pre-programmed mission, and this mission is fully autonomous. As you can see, we've got like real-time view, what's happening, I mean, in the brain of the robots, or in the brains of the robots. But what's very important, the operator has the option that he or she takes the head-mounted display and can observe what's happening in the facility. Obviously, there is still the option to break the mission and drive all the system completely manually. That still is in there. And as you can see, the robots have the 3D view of the surroundings, so the obstacle avoidance and this stuff is still in here. What's also very important, the operator can just by pressing one switch from one robot to the other. As you can see, each of them has different like viewing capabilities. One of them has this articulated head, and the second one solid state. Still, the view or the immersion is more or less still the same. Yeah, and that's all. Thank you very much for your attention.
Thank you so much. Thank you. And congratulations on a very successful project and a wonderful presentation. Ladies and gentlemen, last but not least, we have our colleagues from Germany who you might have seen setting up something in the corner, and it was foreshadowed a bit with the use of VR in the previous presentation. The main speaker will be Tim Schwarz from Dr. Tim Schwarz from DFKI. Also, we will have Dr. Khansa Rekik, and accompanied with Alexis Bernhard from DFKI as well. Khansa is with us from ZeMA, and we're very, very lucky and honored to have all three of you. Tim, the floor is yours.
Yeah, thank you.
Oh, you've got your microphone. You can have this and take it away. Thank you.
Can you make sure that this is on the live stream as well? Thank you. Okay, thank you very much for the introduction. So this is Alexis Bernhard from DFKI Kaiserslautern. Khansa, if you come up, sure. Khansa Rekik from ZeMA in Saarbrücken. So we represent the German testbed. Oh, where's the, here. So quickly an overview. We had several core developments in the German testbed. So that's the basis-conform multi-agent system for distributed production. Pavel just talked briefly about it. Alexis will give some insight later on. But we were also working from the beginning on distributed transfer of control scenarios. So transfer of control quickly is, as Luděk already said, so you can have autonomous robots. Autonomous robots can come into situations that they cannot resolve by themselves. And then they need help of another agent. That agent can also be human. So we showed this already when the German president was here. We showed one demonstration. Later, we showed how we could teleoperate a robotic arm from here in Saarbrücken. And we're doing all of this stuff also using active visual digital twins, where we're using the information coming from asset administration shells and can show it in a very visual, three-dimensional way, which is also very good to do transfer of control. As we will see live in a few minutes, and I want to speed up a little bit because we really want to show that live demonstration. So with that, I would hand over to Alexis, who will talk about the multi-agent system.
Yes, thank you. So let's present a little bit what we do in Kaiserslautern at Smart Factory Kaiserslautern and at DFKI. So we also have our own demonstrator system demonstrating different use cases and different parts, and we are actually part of RICAIP 2. And we typically have a so-called modular demonstrators or multiple modular demonstrators. We like to call them production islands. And on those production islands, we have different modules, for example, quality module or conveyor module. And you can see ourselves, Smart Factory Kaiserslautern, also typically at different booths, at different fairs, for example, at SPS in autumn or next spring at Hannover Fair. We're there each year. Okay, and here I just brought the battery pack use case we presented in Kaiserslautern directly for RICAIP. For example, here we have a quality control module taking images, and with the help of AI, it can actually look at different faults or faulty batteries and detect them. And then this can be transported to different modules. So we have this really modular approach as well with capabilities. As Pavel explained already from the Czech side, we have the same thing, and we also do planning and execution system, and we connect that to our production modules below that. So let's come to that middle area more specifically, namely our multi-agent system. The idea of the multi-agent system is that we combine our modules we have based on the technology together with this network of RICAIP. So you already saw from Pavel this connection. So on the left side here, you could really see here this connector agent makes this connection to the RICAIP network. And then based on this connection, the goal in RICAIP was that we bring our technology to the RICAIP network. And the RICAIP network in terms of here was to actually show our multi-agent system directly at Saarbrücken. So we did not only have this at Kaiserslautern, at our own demonstrator and everything works, but also we implemented that directly in the RICAIP network and then added our concepts, for example, a modular product as well, showing at the Raspberry Pi scenario, just another scenario we were looking at, and then connecting this to, for example, the digital twin developed in Saarbrücken with the asset administration shell, for example. Okay, that's everything from my side, and with that I would hand over to Tim again.
Hey, thank you. This one, thank you. So, yeah, and we used Alex's system also to build a demonstrator at the German testbed, where we were assembling Raspberry Pis into cases. And we had several stations, so one big bin picking station, which was developed by ZeMA. So there were commissioning parts out of the bin that are needed here at the assembly station. We also had a mobile robot, MIR robot, that would bring then the commissioned parts over to the assembly station, and then a local worker could work together, not autonomously, but cooperatively with this robot. So this coordination was done by Khansa from ZeMA. And we also had the possibility that a remote worker from Prague, for example, or from Brno, could virtually go to Saarbrücken and work together with somebody else. And now we had the chance to transfer this knowledge, all that stuff that we learned in RICAIP, closer to the industry in a project called C4Retail. That's an international project between Korea and Germany. So we heard about Korea in Tillmann's, our cooperation in Tillmann's talk. Metra Labs is a German company who build robots, especially scanning robots. So you can see them here in the Czech Republic, maybe in Decathlon, the Decathlon stores, but probably they drive around at night, not during the day. And Kim is building a mobile manipulator, and we as DFKI, we put it all together. Oh, that's a bit blurry. So the idea is that we have a robot driving through the warehouse. Doesn't have to be retail, can also be intra-logistics scenario through warehouse, and it takes inventory of all the shelves and fills up the digital twin with all the information that it sees. And then we can automatically detect if there's something wrong, if there are anomalies, for example, misplaced products or materials, or that a shelf needs refilling. And then the mobile manipulator can try to resolve this. Was resolve the right word, right? To resolve the anomaly and take the misplaced parts out or restock the inventory. And that's what we want to show you live now. And for that, we will switch to a live stream to Saarbrücken. So I hope that this is going to work. And we would also need that laptop on the other screen. The other laptop? Okay, now here's the picture. Okay, thank you. Andy, can you hear me?
Yeah, hello, Tim. Many greetings from Saarbrücken. I can hear you very well.
Okay.
And we are ready to start.
Okay, very good. Thanks, Andy. Please proceed while I'm explaining a little bit. So this is in Saarbrücken. This is our mobile robot. We call him Pickbird. It's a drivable unit again with a robotic arm on top. And on the back, you can see we have some shelves. And when Andy starts the process, so we slowed the process down so I can explain a little bit more what's going on. But as soon as Andy starts the process, we will see how the robot is right over there, exactly. So Amindo, if you could show the digital twin. So this is the digital twin. It gets live information from the robot. Here you can see the planned trajectory. And now the robot has reached the shelf. If we can switch back to the live view again. Exactly. So the robot is now in front of the shelf, and the next step will be to check this middle layer here of the shelf. And we will see the robot going into a position where it can now start our visual pipeline. The visual pipeline will take a picture and then analyze the picture. So if we can show the dashboard, oh, it's already done. So here we see the original picture that the system took. And we can already see as humans, so there's something wrong, right? And there are barcodes. And for example, now, because we cannot, as humans, read the barcodes, we wouldn't know what's exactly wrong. If we show the next picture. So here we see our object detection, detected several objects and also the barcodes. And what now happens in the background is the anomaly detection tries to find out what's going wrong. So if we can see that. And it marked here, that's a little bit hard to read here. So above here, it actually says there are two problems here. One problem is this part here is empty. And the other problem is that here the corn waffles do not belong here. They do not fit with this barcode. And this is a rule-based AI system that's doing this. So it's not an LLM hallucinating about what could go wrong. So this is very reliable. And so the next step is then, if we switch back, thank you, that the robot is now trying to resolve the problem by taking away these corn waffles. And now this is the interesting part. Two things can happen. It can go wrong or it can work. Actually, I'm hoping that it goes wrong because then I can show you the transfer of control, but we have a backup. Oh, it works. So for this, the 2D image that we saw earlier is not enough. It had to take a 3D image to find out the correct position of the item in the shelf, and then it had to decide if it can really grasp that object. And this is very tricky, and sometimes this can really go wrong. So our plan B to show you the transfer of control is, so Andy placed it back, and I can now show you what it looks like if I'm taking over the control. And for this, I need these glasses here, which also means I cannot see you. And I need to start the application. So you should see what I'm seeing, I think, on this screen. This is going to be tricky because my hands are shaking. So here we are, basically in Saarbrücken. Can you see that? Yes. Okay. I can now take over the control with this menu here, activate, and I'm seeing a green, a green light on the robot, which means I can now move the robot, and I'm now looking onto the 3D representation of the robot. And we have a special mode to control this, where the end effector is basically doing what I'm doing with this controller here. And on top of that, you can see this live camera stream there. That shows me the perspective from the robot itself. So what I'm doing now is I'm trying to find a good position for the robotic arm. I'm opening the gripper. Hey, oh, wrong button. And now I'm switching over to a different control mode that makes it easier for me to look on the, on the live image, the live video stream, and control the robot arm there. And I'm going to close a little bit more. And hopefully, without crashing, taking it out. Yep, and I'm switching to the other mode again. And I'm going to place it inside here. Come on, open the gripper. Now. Okay. And, oops, I'm finishing the task. And yeah, so that was the live demonstration. And of course, the idea is then to learn that the system can learn from this grasping action that I just did. So the next time, it hopefully can grasp the product by itself. And it will also be a multi-robot system, so we have one robot that can scan all the shelves, and the other robot will then do all of the handling tasks. So that's it from our side. Thank you very much.
Thank you, Tim. That was amazing. Thank you also to Alexis and Khansa. That was great. And huge congratulations. And we're, again, very happy for this interdisciplinary and international cooperation.